everyone, today I'm going to be talking through some phase diagram calculations with an application at Mauna Loa. So again, you can get this file from the Read the Docs page if you go to examples and under phase diagrams. So again, watch the installation videos. If you haven't, in this video we're going to be using pMELTS, MELTS 1.2.0 and also the green model from MAGEMin. So you need to make sure all of those are installed. So I'm not going to run this live because my laptop is quite slow and phase diagrams require a lot of different calculations, but just going to talk through it like normal. So again, this first cell, if you've chosen this installation method, if you don't have admin rights, you'll load it here. Importing pet thermotools, make sure you're on 3.1 plus. And then again, if you're on Mac, just run this cell twice. That will suppress all those annoying print outputs. And then here I am specifying my primary melt compositions. This was an estimate I did from this bulletin volcanology paper you can look at. So we took the most primitive glass composition, ran reverse fractional crystallization models in Opx-Ol. You could also do those in MELTS if you wanted to, and then estimated what that melt would look like at 20 weight % magnesium. So there's our composition. Then we're going to use this function PTT phase diagram calc. Okay. So there's a couple of things that this takes. So the first thing is a model. So we're going to run pMELTS. And then you also need to specify your bulk composition. So in this case, this was this prime melt or primary melt variable I specified up here. We're then going to specify the range of pressures that we want to search over. So here we're searching from 200 bars up to 15,000 bars or 15 kilobars. Once you go to really low pressure, you might find a lot of convergence issues. That's why I'm stopping at this pressure here. We're then going to specify a temperature, so we're going to go from 1150 to 1450. And then for each of these, you're going to specify a step, effectively. So what this is going to do is take 25 equally spaced steps between 200 and 1500 bars. And that's basically going to define like how high resolution your phase diagram is, or like how pixelated it is. Then there's a couple more important parameters to think about. There's this Imax parameter. What this basically does is it tries to run these calculations and some of them will fail. Imax is how many times it really tries to start again. So basically it's separating these calculations into these sub-processes. This is basically, it will kill off the sub-process and then it'll start again. So in general, 15 is a good start. If you start seeing a lot of holes in your phase diagram, you'll see some of those below. You can increase this a bit. Generally, it's good to maybe run 15 to start with and then see if there's lots of convergence issues, particularly at lower pressures. Then you can set a larger Imax, but it will just take longer to run. And then the final parameter is this refine step. So let's think a bit about what this is doing. So initially, your phase diagram is defined by this array of points. So in this case, we've got 25 equally spaced points in pressure and temperature space. So what it'll do is it'll say, for example, here you have olivine and liquid, here you have olivine and liquid, and then here these black dots would be liquid. So then what you would do is you would put the olivine to olivine plus liquid phase boundary here. You can see this is pretty pixelated. So instead of just increasing the resolution of your grid from the very start, which will take a lot longer, you don't actually need to do that. So what the refine step does is say refine equals 1. What it'll do is it'll make this initial phase diagram and then it'll say, okay, so I know that the olivine to olivine plus liquid phase boundary is somewhere between these 2 points, but I don't know exactly where it is. So it's going to add another point in here. So it's going to add basically all of these red points. This is a new point anytime you're between two calculations that return a different value. You don't need the extra points in here because you got liquid and then you got liquid next to it, so it's very, very unlikely there's a very thin phase field in here. So what it does is it then solves what phase there are, and you can see that would basically cause you to refine your phase boundary here. So this will be after one refinement. And then to make sure that you end up with a grid of points that actually makes sense, because right now you have lots of different X and Y spacings. It's going to cause a nightmare when you try and plot it. It basically just assumes that anything in between two olivines plus liquid is also an olivine plus liquid. Anything in between two liquids is also a liquid. So this would be refinement 1. And then you can imagine for refine equals 2, which we're doing here, you would basically go through and it would add new points between every single one of these that have a different phase on either side, and it would further refine that boundary. So again, the more points you choose, the more refinements you choose, the nicer your phase diagram is going to look, but it's going to be computationally expensive. Okay, so this code is running this for pMELTS. And you can see this is what the output data frame looks like. So to start with, it's just a data frame of 9,409 rows. This is why it's slow, because it's doing an awful lot of these equilibrate calculations. And then your 219 columns, that's the chemistry of your phases, the thermodynamic properties, etc. So where did the 97 come from? Well, initially we had 25 steps in X and Y. That first refined step added 24 new points, so one in between every other point, so that gets you to 49. Then that second refined step added another 48 points. That gets you to 97 in X and 97 in Y. 97 times 97 is 9,409. So then you can use this function, ptt plot phase diagram, and what you do here is you just feed it that output of the phase diagram function here, so this res pMELTS. And what this is going to do is it's going to plot it in pressure temperature space, and down here you can see each field corresponds to a phase. In reality, it is very hard to get phase diagrams looking nice straight out of Python. Matt has tried everything he can. If you have suggestions, feel free to have a go with the code. What I would realistically do at this point is I would then pull this into my illustration program and make the labels pretty after that. And you could decide to label certain phases that are more important. You could decide to emphasize certain phase boundaries. But the underlying calculations are there for you to use. Now, this is actually an interactive plot, and that is because we use this matplotlib widget thing here. It won't be interactive when it's running, so don't panic if it doesn't seem interactive. Just wait for all the calculations to finish. But what this can be nice for is if you're like trying to say like, oh, I can't see what that pixel is, you'll be able to say, you can look here at the bottom, it says a 1,331 degrees Celsius and 1.09 on the y-axis. You have phase 6, which is liquid, olivine, OPX plus CPX. So this can help where you get a lot of boundaries really, really close together and you maybe can't read the numbers or you're not sure exactly what color that you are seeing. Okay, so we're going to do exactly the same thing with MELTS v1.0.2. Actually, this should say, there we go, this was wrong, but we can just change this. So this is 1.0.2. If you wanted 1.2.0, you would just swap these two numbers around. What it's basically printing is these attempts as part of this IMAX. So basically it got to 15 and then it hit some issues and then it started again, basically. So if you had an IMAX of more than 15, this would have taken a bit longer to run because it obviously is hitting convergence issues. And then you can basically see, if you view this as a scrollable element, this was the refinement 1. It hit its 15 attempts and then stopped filling in gaps in the diagram. It did it again for that refinement and then again for that final refinement. So this is one where if you're really worried about the holes, it would make sense to increase the IMAX. That would just give you more opportunities of having solved all of the pixels on your phase diagram, basically. And then again, just feed it to this plot phase diagram calculation. And you can see it's a little bit different. And again, you can hover over anywhere where you're not sure what the phases are. And in general, I would say these are going to be your things. That's where your IMAX is going wrong. So this kind of like funkiness you've got going on here. This is where you can either just like, extrapolate this line and draw it on yourself and say, I don't really trust those calculations. You could also set a little grid going of this area. That would make it faster just so you can see what that's supposed to look like. But in general, when you start seeing these artifacts, that generally corresponds with where you're hitting your maximum number of attempts. So it was just really, really struggling to converge in these regions of the phase diagram. Okay, so for MAGEMin, you can absolutely use the original MAGEMin app. It will be faster, but the point of having this in Python is that we can compare this all in one Jupyter notebook. So it will be a bit slower. You can see again on my incredibly slow laptop, this took 11 minutes. So I just set these 3 running, went and had dinner, and I'm now back recording the video. So again, you can see here, actually, you didn't have nearly as many stability issues as in MELTS. That is pretty typical for MAGEMin. So you can see it actually didn't hit any failures. That's why it only got to attempt 0. It never had to like reorganize cancel calculations into new sub-processes. So yeah, less holes in the diagram, which you can see here. And again, it's interactive. You can see what phases you have in different fields, and you can make this diagram look pretty your own way. So why are we doing this for Mauna Loa? So Mauna Loa has high magnesium number orthopyroxenes, and it was suggested in 2002, based on running pMELTS calculations, that those high Mg number OPXs require very high pressures to form, like sub-MOHO pressures. So when we see high magnesium number OPX at Mauna Loa, it was thought they must come from these sub-MOHO pressures, which then indicates you have much deeper magma storage than we thought geophysically. That did not match with what we found from fluid and melt inclusions, so we really wanted to try and dig into why did pMELTS say that, and do all of the different thermodynamic models agree? So to look into that more, we're not just going to be thinking in pressure temperature space, we are also going to be thinking in mg number space. So for each data frame, I've just added a new column for the magnesium number of the OPX from the MgO and the MgO and FeO content of the OPX. And that's going to help us in a minute. Okay, so as I said, these data frames right now are just a long list of all 9,409 calculations. That doesn't make it particularly easy to plot on a grid. So what this code is doing, this plot phase diagram, is it's kind of reordering these this data frame into these nice X and Y rows. And you might not want to do that yourself because you might want to plot other things. So that's the point of this function, ptt make grid variables from phase diagram. So what you do is you feed it that data frame that the phase diagram code put out. You put what you want as your X column and what you want as your Y column. They will almost always be temperature and pressure. And then it's basically going to gridify every single other variable. So if we run this, we can see that it's going to gridify the mass of grams in the liquid. And then it turns it into a nice array that has as many, rows and columns as your PT grid had. And we're just going to do that for all of them. So we're going to call this X, Y, and Z contains all of those other variables, every single column that's present. We can do that for pMELTS 1.0.2 and the green model. And then what we're going to do to start with is we're going to plot the mass of OPX using this color mesh function. And we're just going to set a min and a max at 0 to 10% because we're really interested in that point at which OPX starts coming in. And also we don't see more than 10% OPX in these rocks. So to start with, we're going to do that for green. We're then going to do it for pMELTS here. And we're going to do it for MELTS 1.0.2. We can just run that. So you can see these white bits, these are where you had some convergence issues. Remember, that's not super surprising at low pressures. pMELTS wasn't designed for low pressure calculations. You can see there are some differences between green and pMELTS. So green starts putting OPX in at about 1150 at 2000 bars, whereas pMELTS puts it more in at like 3.5 to 4. These are reasonably similar in terms of their shape, but you can see the real difference is MELTS 1.2.0. So for example, we can use this interactive plot thing and say, at about 1400, we predict almost 1.1 to 11.2 kilobars for green. For MELTS, we're going to do, it's more like, 1.13, so still high. But then for MELTS 1.0.2, this should be, because I've labeled it wrong, that would be only like 5 kilobars, so pretty different. So let's just replace this because I typed the wrong one. There we go. It's easy to get your 2's and O's the wrong way around when you're typing this. Okay, so the other thing we might want to look at is it can be a little bit difficult to compare these phase diagrams because obviously you can't plot something that looks like this on top of one another from 3 models because that's not going to be easy to see at all. So another thing we can do is we can look for the parts in that data frame, so this original res green data frame before we've gridified it, and we can look for places where the mass of olivine is more than 0 and the mass of OPX is more than 0. And that's basically the phase assemblage that we see in our rocks, so we want to find the places where that's stable. We can also just look at places where just OPX is stable, and then we're going to do that for all of the models. So where pMELTS thinks olivine and OPX is stable, where pMELTS thinks OPX is stable, and the same for that other MELTS. Okay, so then what we can do is we can now plot temperature against pressure, but specifically just for that OPX olivine field and just for that OPX field. So again, it starts to get a little bit difficult when you're plotting multiple models on top of one another, and we need to actually add our legend. So this is where we would say label equals green 2025. This would be label equals pMELTS. And this would be label equals 1.0.2. So we can see that 1.0.2 are these cyan colours. They have this much lower pressure stability field of OPX. And then you can see green and pMELTS look reasonably similar, but again, you definitely see that like 2 kilobar shallowing in the green model relative to pMELTS. And again, you kind of see the same for just where OPX is stable. So you just have some regions where you have OPX but not olivine, for example, in this wedge here. So again, that's plotting in pressure temperature space, which is the more conventional way of thinking about this. We might also want to plot in pressure magnesium number space, for example. So you could try and overlay these. What you will quickly see is that it becomes pretty hard to see. So that's maybe not the best way to visualize this data. Like I'm struggling to there see exactly where the black points and the red points are. And once you start overlaying the cyan data, it becomes even more challenging to see. So what I decided to do here is instead split this into 6 subplots. So first of all, we're going to plot green on its own plot where OPX is stable and where olivine is stable. And actually this should be OPX stable. And then basically do this for all of them. And you'll see what this looks like in a second. So we can see for green, we have this, if we think in terms of our Mg number now, what the original argument was based off magnesium number 86 OPXs. So if we look up here, we'll see the magnesium number 60 OPXs in green can come in at about 4 kilobars. In pMELTS, they will come in at about 6 kilobars, which was what the original study basically said. They were your sub-MOHO depths. And yeah, in 1.0.2, they can come in, again, relatively much shallower. So this basically shows there's a pretty big difference in pressure between these models. This model is run with that primary melt at 20 weight % MgO. This is even more drastic change when you run this at 16 weight % MgO. So in general, this can be very, very useful for exploring differences between models, not just looking at it in terms of a regular phase diagram, but starting to plot different components against pressure, against temperature, and comparing what they look like. If you are faced with a problem like this and you're like, okay, well, my samples are at magnesium 84 OPX and I'm really concerned about these massive differences, that's when you would want to maybe start using the equilibrate calculations to assess which model you think is recreating your experimental data better. And that'll be the topic of a future video, so stay tuned.